for energy method, the basic things that I covered, and also Dr. Mustafa Sani covered, and those are the things that you expected to know is, this is basically energy method to solve, energy method for solving structural mechanics problem. And this energy method is one of the methods that I'm going to talk about, is also used in EAS663, okay? Namely the Rayleigh-Ritz method. Okay? So here, energy method, we are using the method of principle of minimum potential energy. Okay. Principle of minimum potential energy. These are the methods that we use, and this one basically says pi total potential is equal to strain energy plus potential energy of external load. And this one, we cover three basic. This is strain energy due to bending, it's half EI d2v dx2 square dx. This is for bending. If it's a beam problem, then this is the thing that we need. And if it's a bar problems, and if you have a twisting problem, then half Gj d theta dx square dx. Okay. So this have similar form. Okay, EI d2v dx2, EA du dx square, and then d theta dx. Okay. These basic equations are the things that we need when we want to solve this. And this, the other one, this is the potential energy of external load. So if it is a point load, then it's negative P multiplied with the corresponding displacement in the direction of P, or if it is moment, then you have to multiply with theta. If this is point load, if it is distributed load, then you have to do the integrations. If this is distributed load, this is talking point load. If this is distributed load, and then this is the displacement field, this is the displacement field that we are trying to solve. Okay, then this is the equation. If it is distributed load, then you have to do integration to get Vp. If it is point load, just a value negative of that point load multiplied with the corresponding displacement in the same direction of P itself. Or if it's a moment, the negative of that moment multiplied with the rotation at that point of the moment in the same directions of the moment. Okay. There must be a negative here. Okay. And in this equation, P delta is assumed in the same direction. If P acting down, delta is acting down. So this is the thing. If delta is acting up, then this delta also we must put negative. This negative is from the definition of total potential energy of external load. So these are the things that you need to know. And according to principle of minimum potential energy, this is 0. And this means that del pi p del di equal to 0, and di, where I is equal to, I is 1, 2, 3 until n. This is the degrees of freedom. Okay? Degrees of freedom. Example, if I have a beam problem and I have d1 sine pi x over L plus c2 sine 3 pi x over L. So this d will be C1 and C2, 2 degrees of freedom. If it is a displacement axial problem A x plus Vx squared plus Cx cubed, for example. This is the displacement field for the problem that we want to solve. If this is bending problem or this is actual problem, it can be any kind of problem. But this means that we have to carry out this partial differentiation equal to 0 with respect to each of the degrees of freedom. So here we have to do del pi p del C1 equal to 0, del pi p del C2 equal to 0, and solve these two equations to get C1 and C2. Here you have to differentiate 3 times, one respect to A, second one respect to B, the third one respect to C, and solve the 3 equations to get ABC. And you get ABC means you get the answer. Okay. Now, these are the main things that you, in energy method, that you need to know. The expressions for strain energy bending. So beam problem is this, bar problem is this. This is twisting. Twisting we don't cover so much. Okay. So bar problem is this, beam problem is this, and this is the displacement, lateral displacement of the beam that we assume. And this is U is the actual displacement for the bar problem that we assume. Then we need to add this together. Then we need to apply this principle, meaning that we need to get this set of equations. So depending on how many unknown coefficients or the degrees of freedom of the problem, then we have to solve. If 1 degrees of freedom, only 1 equations straight away. If 2 degrees of freedom, then 2 equations. 3 degrees of freedom, then 3 equations. So this I go through with you in general. So next, if we cover principle of minimum potential energy, we use it with one method that we call the Rayleigh-Ritz method. Okay? We make use it together with a method that we call the Rayleigh-Ritz method. The Rayleigh-Ritz method is an energy method. Rayleigh-Ritz method is an energy method that we use to solve a problem, where we make use of principle of minimum potential energy. So Rayleigh-Ritz method, you need to assume the displacement field. So this displacement field, meaning that we make assumption about the solution first. We make assumption about the solutions, specifically about how the solution, the shape of the solution, but we don't know what is the actual value at a certain point, and we use the energy method to help us to find that. So we assume the displacement field. So displacement field must be assumed. So it can be, for example, psi pi x over L or psi 3 pi x over L. So this is the displacement field for a beam bending problem. Or if it is an axial displacement problem, maybe it's just AX plus BX squared. So this is also a displacement field. This is for bending problem, let's say V, and this is for axial problem, let's say for this bar problem. Then you have to make sure that this is kinematically admissible, meaning that it satisfies the boundary conditions. It must satisfy the boundary condition of the problem given to us. Only the displacement boundary conditions. Only the displacement boundary conditions we must satisfy. Which means when you substitute x corresponding to the location of the boundary, then it must give you the value which represents the boundary. If it is fixed, then you substitute x is equal to 0, u must be equal to 0. When you are substituting in the displacement field. So this is called kinematically admissible. So next step, after you do this, what you do is you go to After this, number 2, then we evaluate, you get the total potential energy, which means you need to get the strain energy. And so here, as I mentioned, it depends on bending problem, axial force problem, then the strain energy will be accordingly we have to use. If there is a bending problem plus axial problem, which is there is a beam plus there is a spring. There's a spring somewhere at the support, near the support, supporting the beam. So that spring will change length. This is axial deformations. And the strain energy is given by this. Or for spring problem, the strain energy is just equal to this. Okay. For spring, half K delta is what is the elongation of the spring at that, what is the elongation of the spring? Okay. So this is the next thing. Then after that, this involves a lot of differentiation first, then integration. So this is a very time-consuming process. So please be careful with the differentiation that you do, and after that, integration again. Okay. Then the next thing that you do is you apply this, meaning that you have to do these partial differentiation equations depending on how many degrees of freedom that we have. Then we solve. Then only you solve for this di. So once you solve for di, then you get the solutions. So this is the basic things about Rayleigh-Ritz method. So Rayleigh-Ritz method, if you are asked to use a particular displacement field which already given to us, you have to use that displacement field. If it is not given to us and you are asked to solve that, then you can assume. If you're asked to assume linear field is only one term. For axial problem, it is a quadratic field, then it is the second term here, quadratic. But if it is a assumed displacement field already stated, given to you, then we have to make use of that. And then if you ask to check if it is kinematically admissible, then you have to check. Checking kinematically admissible means make sure that the boundary condition, the kinematic boundary condition is satisfied. Then go to this. So try to recall how to get this. Bending problem is this, axial problem is this. Then know how to get the potential energy of external load also, depending if it's a point load or it is a distributed load. Then go to this, which is the main thing, principle of minimum potential energy, which means you have to, after getting this, differentiate it partially with respect to each of the degrees of freedom. Then you get 2 equations or 3 equations to solve. So solving equation also can take some time. Okay, so try to be familiar how to solve 2 equations fast. Or then after you solve for this, then you can get the displacement that you want to find. Okay. So basically that is what energy method is all about. Okay, and you need to know what are the strain energy equations that you need to use. Okay, don't forget the square, don't forget the EI. Okay, and differentiations 2 times, square again, and integration, so takes very time consuming. Very time consuming. So be familiar with the differentiation first, then integration. Sine, cosine, how to integrate. Okay. X square, polynomial is easy. If you sine, cosine, a little bit time consuming. So that is energy method that I would like to refresh with you. Okay, I will not be able to go a bit deep into all the basic steps, but you have to go to the notes and then recall how to get this, to look at the relevant equation, and also to look at potential energy of external load. Okay. So